Okay, this is example 9. This is the last example we're going to do, and then we're going to assign homework assignments. So this, another twist, we're doing all the little different things we can do with these problems, and this one's a very real-world application. It's a simply supported beam with a universally distributed load across it, just like a floor joist would be. But suppose in the middle of that floor joist with all the other furniture and everything else you have on that floor, you have a really heavy object. Maybe you have a safe or something very heavy that's really pushing down in one place, and you want to know what the effect with the UDL and a peak load somewhere else is having. So this is a pretty good application. All right, this should be nothing that you haven't seen before. Basically, you gotta, in order to get the reactions RA and RB, you gotta convert this UDL to a concentrated load. If you do that, if you redraw it just right here, this is the 3,200 pound force right there. 25 pounds per inch over 120 inches is an additional 3,000 pounds. So 3,000 pounds plus 6,200 pounds acting solely in the middle. From inspection, you could see that if the total is 6,200, then each one, RA and RB, must be equal to 3,100 going up and down. Okay, so that's the reactions. That's what we need to go on. We're going to solve this the traditional way in shear moment diagram. Okay, so just bear with me for a sec. Okay, so we have it set up here. Same thing. Notice the concentrated load and the distributed load. We're going to use it just like we've been doing in the past. So, for example, let's just do the shear as fast as we can. Just a quick way. We know that if RA is going to shoot up to 3,100, our shear is going to go up all the way to 3,100, right? Now, what happens with the UDL, right? The UDL goes down linearly, the amount of the UDL. If this load weren't here, this 3,000 pound UDL, it's net 3,000 pounds, would just go from 3,100 all the way down to this minus 3,000, you'd end up here. But you have to do something once you get to the point where this is acting, right? So from 3,100, we're going to go half the distance. Half the distance, 25 pounds per inch over 60 inches gives us what? 1,500 pounds. So it's a net from here to here, we're going to go down 1,500 pounds. So we're going to start here, and we're going to go down our final value. 3,100 minus 1,500 gives us 6,100. I'm sorry. Gives us 1,600. And we're going to go down in that same linear fashion. It's going to go down in a first order way, first order straight line to there. Okay? Now, once you get the UDL to here, all of a sudden you're going to shoot down another 3,200, right? So 1,600 minus 3,200 gives us what? A negative 1,600. Why do I keep drawing this wrong? God, sorry. Negative 1,600. This total span is 3,200. So then we're going to go straight down that amount, right? And then once we're there, we're going to continue down with the rest of the UDL, the 25 pounds per inch over the remaining 60 inches. And that is half of that, which is 1,500 pounds. So 1,600 minus 1,500 takes us down to negative 3,100. So once again, we're linear because that's a zero order. We got to go down linearly like this. And at 3,100, we get the reaction at B, and we close off, right? Okay, pretty easy. So now this shape becomes a little something new, right? It's basically the shape of a UDL with an interruption. Every time you go here, you interrupt and you shoot down. We could put other concentrated loads here. And every time the UDL would get to it, you'd have to jut down the amount of the load, right? That's basically it, okay? So now how do we get the moment, right? So we're talking about areas here. So we can break these into different amounts, but let's go through it as we go. So at point A, all right, we have VA is equal to the reaction is equal to 3,100 pounds. No big surprise, that's that value right there. MA is 0. We've said that a bunch now, right? I want to know what's going on at point B, which is all the way at the end. Well, before I get to point B, I kind of have to know what's going on here. I have to go from left to right, so I can't just go from here to here. I have to do something else. So I'm going to call this point C. So I'm going to put here point C and do that one first. Okay? So at point C, I need to know, right, the slope of the UDL, right? So I need to know where, basically what this area is, right? So my moment value here, wherever this is going to be, my moment curve, I know it's going to be, if this is first order, I know I'm going to be basically parabolic to some number, right? This is going to be second order. The question is, what's this value right here? This value is the value of trapezoid AC. Okay? AC, you can break up AC into two basic shapes, right? You have what? You have a rectangle, right? And you have a triangle. So you can say it like this. You can say that the moment at C, which is that point right here, is equal to the moment at A, which was basically, sorry about that, which is basically 0. And this shape, these shapes are above the axis, so you're going to say plus area AC. But AC is what? Trapezoid or triangle plus rectangle, right? You can do the trapezoid, that's harder. I'm going to do the rectangle triangle method, right? So you can say simply here that MC, right, is equal to, 0. Let's do the rectangle first. 16, base times height, which is 60 times 1600, 60 inches long. The height is 1600, so we'll go 60 times 1600. Now the triangle is what? Base times height over 2. The base is 60. The height is, the difference from 1600 to there is what? 1500. Divided by 2, we get a value of 141,000 pound inches. Okay, so we know this is going to be 141,123 right there. Okay, let's also get the shear at C, right? We already know what it is. It's going to be that and that. It's going to be both. VC is equal to 3,100 minus 1,500, and that gives me 1,600. So what's the value at C? It's really both, right? So the shear value at C is anywhere between 1,600 and minus 1,600. The important thing is the shear force is 1,600. Whether it's going one way or the other, it's still a value of 1,600. So that's the answer to that. So now that I know the moment here, I want to figure out what's going on at B. So I can go back to B. I'm sorry, all this here, right? This should be here at point C. Well, let me cross out point B. I'll do point B right here. So at point B, let me go back. Okay. At point B, the UDL goes down another 25 pounds per inch times 60 inches, and that gives me 1,500. It's going down, and it goes down to negative 3,100. Therefore, my shear at B is equal to minus 3,100. We just did that. That's just the math behind how I got to that point, and obviously with the reaction, we're going to close back up. But MB is pretty easy, right? The moment at B is equal to my old moment, or my previous moment, which is C, and this area here is below the axis, so that's going to be minus area CB. This is also a rectangle and a triangle, right? So we can say that MB is equal to 1, 4, 1, 1, 2, 3, correct? Minus, and base times height over 2. Let's say the rectangle, the base is 60. The height is 1600. The triangle is the base is 60. The height is 1500. And that's divided by 2. We're going to find that that's equal to 0. So, no kidding. This has to close up parabolically to there, right? So this is also going to be second order, right? That's my moment diagram for this problem. Where's my peak? Right there. So my M max is equal to 141,000 pound-inches. Right? Basically, this one's pretty easy once you understand it, right? You could have a UDL that you're constantly declining. Every time you reach concentrated load, you're going to dip, right? So, for example, if I had a load right there, I would go down my UDL, then I'd dip down, continue my UDL, dip down, keep going, right? So you can see the motion or the way the load works is, it's pretty easy. This one looks tricky at first, but once you understand the mechanism of how this all works, it's actually pretty easy, and it's always going to turn into a combination of two shapes, a triangle on top of a rectangle. So once again, any questions, feel free to ask, contact me, and this is the last example we'll do. There are 5 additional homework problems I want you to try, and I'll go over those the beginning of the next class. Okay, thanks.